I'm Minae, and I'm going to talk about how we can model humans under risk. It's important for robots to be able to understand and anticipate human behavior to create seamless human-robot interaction. One way to do this is to build models of human decision-making. But in many other scenarios, modeling humans is not as easy as you think. For instance, consider a scenario where an autonomous vehicle in red wants to make an unprotected left turn, but we see a blue human-driven car approaching. The light just turned yellow for the human-driven car, and we don't know whether it will run the red light or stop and play it safe. The blue car's actions will determine what actions the red car can take. Now, if the robot assumes that the human driver is purely rational and is going to make decisions like how it would make decisions, it would think that the driver would stop. The robot can then try and make the left turn. But it's not uncommon for cars to run yellow lights. I'm sure all of you have seen that in real life. Clearly, the robot misjudged the driver's decisions here. So what are we missing? What's really going on is that humans have cognitive biases and aren't perfect. If you're building robots that are interacting in risky scenarios, they should be able to model human suboptimalities. So in this work, we looked at how robots can model human decision-making under risk. First, we formalize how we can create models of humans that incorporate risk. Next, we also look at when we should be using these risk-aware models. And finally, we explore whether these models can improve the quality of interactions. I've organized the rest of my talk around these contributions and we'll step through them one by one. First, let's talk about our mathematical formalism. We assume a setting where the human needs to select an action from a discrete set of actions. For instance, the human could choose to accelerate or stop. Taking an action may lead to several possible outcomes. For instance, accelerating can lead to making the light or running the light. Each outcome has an associated reward that the human receives, as well as an associated probability of happening. We can then express the expected reward as such. Let's visualize some models. On the x-axis, we have all the possible actions a human can take, and on the y-axis, we have the probability of an action. The probability of an action can also be expressed using the Boltzmann model. Now let's say that the action that gives us the highest expected reward is shown by the dotted line. One way we can model humans is to assume that humans are like robots and are rational decision makers. This means that humans are assumed to always select optimal actions that maximize their expected reward. But we know that this isn't always true. Sometimes humans aren't perfect and choose suboptimal actions due to factors like limited cognitive resources or time. This is commonly referred to as the noisy rational model. Under this model, humans choose the optimal action most of the time. The noisy rational model is currently the most prevalent way we model humans in HRI. But one problem with this model is that no matter how much we tune model parameters, suboptimal actions will never be the most likely action. For instance, going back to our driving example, what if some other action that is not optimal is actually the most likely, like choosing to run a yellow light? We propose using a model that captures this suboptimal behavior as shown by the orange curve. Specifically, we use cumulative prospect theory, or CPT, which has been widely used in behavioral economics. Remember how this is the expression for expected reward? With CPT, what's important is that we aren't really introducing a completely new model. We're still optimizing expected reward, but human suboptimalities are explained by nonlinear transformations and probabilities and rewards associated with each outcome. We'll step through both of these transformations, starting with the reward transformation. Here's an example of how CPT transforms rewards. The dotted line represents the ground truth reward, and the orange line represents our model. What's cool is that we're adding just 3 hyperparameters to the original reward to express the fact that humans perceive the slope between large rewards, as shown here, to be smaller or less steep than the slope between smaller rewards. For instance, the difference between $1 million and $1.1 million will seem smaller to most people than the difference between $1 and $10,001, even though they're the same. CPT also transforms probabilities. Without loss of generality, let's say our rewards associated with each outcome are positive. Here we introduce one parameter, gamma. This transformation says that humans overweight smaller probabilities and underweight larger ones. For intuition, take playing the lottery. Even if the probability of winning is almost 0, we buy tickets anyway thinking we have a much larger chance. So this is how we get our transformed expected reward. We now know that risk-aware models have the capacity to model suboptimal decision-making, but we still don't know when we should use these risk-aware models. In other words, when do humans act suboptimally? We conducted a study based on our running example. We told users to imagine that they are on their way to return a rental car, but the stoplight turns yellow. They can choose to accelerate and risk paying a $500 fine, or stop and pay a late fee. Here are some factors that we thought could influence how humans make decisions. Information about the likelihood of the light turning red, the amount of time users have to decide on an action, and the risk involved. We varied these three different things and asked human drivers whether they would accelerate or stop in each one of these scenarios. First, let's look at how frequently participants chose each action. You might think that all factors would influence users' actions, but we were actually surprised to find that users always chose to stop at the light no matter what. However, the factor that most clearly highlighted when users made suboptimal and optimal decisions was risk. In high-risk scenarios, when the light frequently turned red, stopping was the optimal action, and as you can see, most people acted optimally. In low-risk scenarios, when the light rarely turned red, accelerating was the optimal action, and as you can see, the majority of participants actually acted suboptimally. Since people behave optimally in some scenarios and suboptimally in others, we really need our robots to be able to anticipate both optimal and suboptimal behavior. We next wanted to see if our robots could predict these action distributions by learning the model parameters needed to be able to reproduce them. We computed the noisy rational and risk-aware models that best fit our action distributions. To measure the accuracy of these models, we compared the KL divergence between the true action distribution and the model's predictions. On the left, when humans make decisions that we might expect, both models do well. But when humans are suboptimal, here is where the risk-aware model really shines. On the right, you can see that the risk-aware model was able to better capture the user's tendency to make suboptimal but safe choices. We now know that risk-aware models can better predict suboptimal human behavior, but why is this useful? To test the usefulness of the risk-aware model, we performed a user study with a robotic arm. Participants performed a collaborative cup stacking task where the human and robot are trying to stack these 5 cups into a tower. There are 2 possible configurations. The first is an efficient but unstable tower. It is unstable because we programmed the robot to accidentally knock it over 80% of the time, but it is efficient because it requires less robot movement. Users were awarded 105 points for building the unstable tower. The second is an inefficient but stable tower, which never fell but requires more robot movement. Users were awarded 20 points for building the stable tower. If either tower fell, the team received 0 points. Looking at the expected rewards, we see that building the efficient but unstable tower is actually the optimal decision. Because the unstable tower leads to higher expected reward, a noisy rational robot would assume that humans will want to build this tower. In our experiment, each participant was given some time to practice building towers with the robots and learned about the probabilities of each type of tower collapsing. During test time, users built the tower once with the noisy rational robot and once with the risk-aware robot. We measured efficiency and safety during collaboration. Planning with the noisy rational and risk-aware models led the robot to choose 2 different trajectories. Let's walk through what happens when we use the noisy rational model. In this diagram, you have the robot arm on the far side of the table and the participant's hand on the near side. The participant goes to grab the orange cup in order to build a stable tower. The robot incorrectly assumes that the human wants to build an unstable tower and reaches for the same orange cup. Meanwhile, the human has already stacked it. Realizing that it made the wrong prediction, it has to replan and pick up the other cup and then stack it. Here is that same scenario played out in an experiment trial. You can see that the noisy rational robot causes the user to flinch and the robot has to replan. Instead, a risk-aware robot can correctly anticipate that the human is overly concerned about the tower falling. When the human reaches for the orange cup, the robot reaches for the purple cup and then stacks the cup without colliding with the human or having to replan. In practice, you can see that planning with the risk-aware model creates a much smoother interaction. In sum, we propose using risk-aware models like CPT to accurately model suboptimal decision-making. Thank you.